welcome to today's webinar, everybody, on refrigeration, getting the basics right. This is James Neal, and we're joined today by Dr. James Carson from the School of Engineering here at the University of Waikato, and he's going to be our presenter for today. So just a few housekeeping things before we get started. A reminder that if you've got questions, by all means feel free to put them into the question portal as we go along, and there'll be some further bits and pieces at the end of the webinar. And just to reiterate, today's webinar has been recorded and will be available for future download from the ECA Business YouTube portal. So on that note, James, I'll hand over to you to get us underway.
Okay, thank you, James, and good morning, everyone. Thanks for joining in. Just go through a there we go. Just go through an outline of this morning's webinar. Start with a relatively brief introduction, and then we'll have about 4 themes of discussion about how to run your cold store or chiller or freezer, refrigerated facility as effectively as you can. And we'll finish, it's not listed there, but we'll finish with talking about how to monitor or how you can improve or identify areas that need improvement. So first of all, hardly need to tell anyone, and I'm sure that refrigeration, isn't it? Okay, so we're just having a technical hitch. Have I not? Do I need a? Okay, so sorry about that. Yeah. Okay, hang on. Got to press play. So yeah, we'll just run through a brief introduction and go through 4 different things about managing a refrigerated facility, and we'll finish with talking about how to identify ways to improve your efficiency. So obviously refrigeration is vital for New Zealand's economy. It's not a very glamorous industry, but all the same it's vital. Every food item gets refrigerated at some stage. So without it, we'd be in a bit of trouble. And of course, more and more worldwide, refrigeration's vital for feeding the growing population. What it does allow for is to balance or buffer the effects of seasonal production of food with the constant year-round demand of food. And one of the ways that we're going to have to improve, arable land is used up, so to make sure that we can feed ever-growing populations, we have to reduce the wastage, and part of that is through improved use of refrigeration, particularly in developing nations. So, most people walking down the streets don't think there's much to refrigeration. You open the door, you put your can in, and you close the door, and then a bit later on it's cold. But of course, it can be done poorly, or it can be done well. Now, we're going to be limiting our discussion to the vapor compression cycle, since that's the vast majority of how the vast majority of refrigerated facilities are cooled. So this is a graph from Statistics New Zealand. It's a few years out of date, but you can see right at the top, in terms of the total industry energy use, the food, beverage, and it says tobacco, although that's a drop in the ocean really, isn't it? Right at the top, and I don't think that trend would be any different 4 years after the fact. So clearly, food, beverage industry consumes a lot of energy, and I'm pretty sure that drying and refrigeration would be the top 2 in the list of the particular, if you were to break that usage down, the drying and refrigeration, that would be the 2 biggest players. So if we can improve just marginally across the board, that's significant savings nationwide. So when we talk about refrigeration, we always need to bear in mind the first and second laws of thermodynamics, and the first one is about the conservation of energy, and of course heat and mechanical work being different manifestations of the same thing. But importantly, we need to recognize that you can't beat the first law. In fact, someone summarized the first law as saying you can't win, and the second law is saying you can't even break even. So that's important. I think of one illustration from where I used to work. There was a building with some internal offices which didn't have windows outside, so they had, well, they're supposed to have air conditioning. On a really hot summer day, everyone was complaining, so they looked up in the roof and they found that there was one tiny unit which just had four different flexible ducting tubes going to the different offices, and they weren't insulated, so it was horribly undersized. It's like someone just thought, I have a refrigeration unit, as long as I touch it, everything will be all right. You need to know the quantity of heat that needs to be removed. You can't just have one device making something cold and thinking that it can work with infinite effectiveness. Now, the second law tells us that heat only flows in one direction, from a high temperature to a low temperature, and yet refrigeration, of course, is achieving the net effect of taking heat from a low temperature to a higher temperature. Now, the way it works is it changes temperature without transferring heat. So when you compress your refrigerant, you don't add heat to it. Instead, you increase its pressure, and as a result, its temperature also increases. Now, we also need to make a distinction between heat and temperature, which, of course, most people walking down the street don't need to. But they're different manifestations, again, of the same thing. So heat is a quantity of thermal energy, and it's measured in joules or kilojoules or BTU, British thermal units, or calories, or a variety of others. And then there's temperature, which is an intensity, or you might describe it as a quality of thermal energy. And you need to remember those two are different things. Okay? So let's look at a diagram of a typical vapor compression cycle apparatus. The four essential components, of course, are the compressor, the condenser, the expansion device or a valve, or it might just be a restriction in the line, and the evaporator. Now, most cycles will also have various other components. Most will have some sort of filter or dryer to protect the compressor. Normally there will be a receiver, or basically a refrigerant store for excess refrigerant in the cycle. And then what I call the accumulator, some people also call that a receiver. That's just another device that protects the compressor from droplets entering into it. So if there's any liquid coming out of the evaporator, it'll fall down to the bottom of that accumulator and evaporate before it goes into the compressor. So obviously, just with running your cycle, you should have your low pressure lines insulated. So that's between the expansion and the compressor. Now, often you'll have the expansion valve very close to the evaporator, but also the lower the temperature going into the compressor, the less work that will be required. And that's why in multi-stage compression you often have intercooling, just so you can reduce that work. So it is important to keep those low pressure lines insulated, whereas the high pressure lines, it may actually be better often to leave them uninsulated. We need to make a distinction between chilling and freezing, because if you get that wrong, you'll be in trouble. Generally, of course, the lower the temperature, the longer food will keep, because it slows down the rate at which microbes grow and at which enzymes do natural affect the color, texture changes, and if it's lipids, oils and fats, it affects the rate at which they become rancid or not. However, of course, you can't just have everything stored down at minus 40 degrees. For example, bananas don't like to go below 10 degrees. Apples and kiwi fruit, you don't tend to freeze those. So you need to keep those at chilled temperatures, whereas most meat and likes of butter, for example, you will freeze them. So it's important to keep those two processes separate, even though the same refrigerated facility will be able to do both chilling and freezing, quite probably. Another distinction we need to make is between temperature holding and temperature pull down. So I've got a diagram, let's say it's a meat. The freezing works somewhere. Your temperature pull down is supposed to be done by your blast freezer. So they'll have a relatively small volume but with higher air velocities. And they may be continuous or they may be batch. But importantly, they'll want air to go around. If it's a carton freezer, they'll want each carton to be exposed to air on all sides. Once it's down to temperature, you'll take it out and you probably put it in a pallet with others and put them in the pallet storage area. So the difference between the two is that the freezer or the chiller, the unit designed for pull down, will have relatively high cooling capacity per unit volume, whereas the storage area is going to have a much larger volume and not as much refrigeration capacity per unit volume. And it's important to recognize that you don't want to overload a cool store or a cold store. It's not really designed for pull down. So if you fill it full of warm product, it's going to struggle. So what can we say about product loads? If it's chilling only, so if that's chilled lamb, chilled beef, horticultural products, you can actually work out the chilling load relatively simply. So the chilling load I've called here Q. You just need to know the mass of the product and also the packaging, because that'll typically come in warm as well. Then you need to know the specific heat capacity. Now for foods that are likely to need refrigeration, they tend to have high water contents. So the value will typically be between 3,000 and 4,000 kilojoules per kilogram Kelvin. So if you just take a conservative value of 4,000, then you just need to know the initial temperature, an average temperature, and then the final temperature that you want. So those are relatively easy quantities to measure. If you measure the mass, the initial, know what the final temperature is going to be, multiply it by 4,000, and that will give you your heat load fairly simply. Now to work out...
Sorry, James, just to make sure that we avoid some confusion there. You said 3,000 kilojoules, but you said 3,000 joules. So if you want to just backtrack and just to make sure everyone's clear on our units here, I'd hate to give someone the wrong...
Thanks, James. I'm always doing that. Normally I work in kilojoules, and I thought specifically not to do that. So it is definitely joules. Okay, so you use 4,000 joules per kilogram Kelvin, and the reason I'm using joules rather than kilojoules, so let's say you have 1,000 kilos, you take your 1,000 kilos, multiply it by 4,000, and then let's say your initial temperature is 22 degrees, and your final temperature or target temperature is 1 degree, it'd be 1,000 kilos times 4,000 times 21, and that would give you your heat load. Then, of course, you divide it by your time. Oh yeah, sorry, the heat load in joules. Yep, Q is in joules. And then if you divide by the time required in seconds, that will give you your average chilling rate. So that represents the minimum cooling power that you need. Okay? In reality, you may not be able to achieve that cooling time, but if that is your target, that will give you your minimum cooling rate. So if you, minimum required cooling rate, I should say. So if your refrigeration unit can't handle that, then you know you're gonna struggle. You might have to reduce the load that goes into that chiller. Okay, now freezing is a bit more complicated because you have the formation of ice. Now it doesn't all, unlike water where the ice freezes at 0 degrees Celsius, all of it, and it won't go below 0 until it's ice. When you have a food product, because the water is dissolved effectively in that food product, you have freezing occurring over a range of temperatures. So you might have the initial freezing temperature, what I call TF, which for foods is typically between -1 degree Celsius and -3 degrees Celsius. But not all the ice freezes at that temperature, and ice continues to form as you go down. And even at -40, you won't necessarily get all the water in the food product being completely frozen. So what I've called M sub FW, the mass of frozen water, itself depends strongly on the product temperature. So I won't go into too much detail with that now. At the end of these slides, there are some references which will go into more detail if you're interested on how to do those sorts of calculations. They can be done quite manageably. It's just that it's a bit more involved than the chilling load freezing, where it really is just 3 numbers multiplied together. So that's the load due to the product. You need to recognize that in your refrigerated facility, whether that's a store or for temperature pull down, some products will respire, so they give off heat of respiration, particularly horticultural products, apples and kiwi fruit. If you're entering product into a facility which has not had the compressors going, so it might be at room temperature, you have to recognize that if you have concrete, you have steel rails, they will take cooling down as well. So you need to add them to the calculation if you are starting from ambient temperature. Heat will come in through the walls, floor and ceiling. That's where, again, you need to have good insulation to minimize that amount. And of course, there's inevitable heat coming in with the door openings, and we'll talk about that more later on. Another significant source of heat is the evaporator fans. Now, you need those, but what we'll talk about later on is recognizing that there's a point of diminishing returns with those evaporator fans, because they cost you in terms of the power required to run them, but you also are adding heat to the environment which needs to be removed. And then, of course, lighting. If you have a lot of lighting, you can't ignore that. And finally, there's defrost heat, which, again, is a necessary evil. But on a well-designed, well-maintained facility, these should be small by comparison with, well, certainly for a chiller or freezer, these should be small by comparison with the heat load from the product. For a cold storage or a cool storage facility, then those other, these factors become, particularly defrost heat and heat infiltration, become significant. So let's summarize some points about the heat load. Important to recognize that cool and cold stores are not designed for temperature pull down. Now, you get examples of refrigerated shipping containers being filled and then turned on, and sure enough, when the product gets to its destination port, it's spoiled. So the refrigeration unit on a reefer container can handle a little bit of pull down, but it's really supposed to be loaded with product at temperature. When you are dealing with a chilling or freezing problem, the heat load doesn't solely depend on mass. It also depends on how much temperature pull down you have. So, for example, you may have 1 ton of product requiring, 15 degrees pull down, and another ton requiring 30 degrees pull down. Although they both weigh 1 ton, the first job only has half cooling load of the second. So the temptation for people is to look into their chiller or freezer or cold store and say, look, there's all that room, why don't we fill it up with product? But you have to recognize that it's not just the volume, the mass of the stuff in there, it's how much heat is in there, okay? So that's, I guess, the most important message, which some people clearly have not received, is you can't overfill chillers and freezers. Just because there is room doesn't mean that you should put more product in. Quite apart from the capacity of the refrigeration unit, you also need to allow for air movement. And that's the next, or one of the next factors we'll discuss. So we've worked out how to calculate the chilling load and the minimum refrigeration capacity. Now we need to consider the cooling process. Let's consider an individual apple needing to be cooled. And when to be completely cooled, you want to cool that center of the apple. So the heat needs to flow from the center of that apple to its surface. Now if that apple happens to be at the center of a carton of apples, once that heat has got to the surface, it has to flow through an air gap and probably through other apples. if there's flow through the carton, then the heat can effectively go around the other apples. But if those gaps are stagnant, then the heat basically has to go through the other apples. So you get that situation, heat flowing from the center of a carton to the surface. Now, with horticultural produce, they just about always have air vents, and hopefully there's a bit of airflow through those vents. But of course, that carton probably will be part of a pallet. So if you're at the center of those pallets, you've got to get, the heat has to go through that pallet and out through another pallet, unless of course the air vents are allowing it to go bypass. So I'll just indicate that here. If the air vents are working well, then the heat will just go out through here, which is the incentive for having, certainly for horticultural produce, as they do produce heat of respiration, those air channels. Of course, if those channels are not aligned correctly, if you haven't aligned the boxes to allow air from outside the pallet stack to go right through, then of course it won't work as well. Then of course, you may wrap your product in plastic film. So probably not so much with horticultural products, because that would defeat the purpose of having the air vents, but perhaps something like butter or cheese, you'll have that extra film wrap. Now it's important to recognize that that wrap is another resistance that heat has to pass through. Okay. Finally, we need to represent the movement of the air from the product surface, the external product surface, so in this case the outside of the wrap, to the evaporator coil, if it happens to be up in one corner of the room. And of course there are a wide variety of designs, and some refrigerated facilities have direct expansion coils going all across the roof. But in this case we're assuming that the evaporator is up in one corner of the room. So how do we model this process? Well, we represent the heat transfer, so this is a heat transfer rate in watts, as a ratio of the driving force, and that driving force is the temperature difference between the evaporator coils and the product itself, and a number of resistances. So we need to consider the resistance of the product itself from the center to the surface. Then we need to consider any trapped air within the packaging, then the packaging itself, and lastly, convection. So what you need to recognize is that changes to packaging will affect your cooling process. So that's one trap that has befallen some people. They put that extra layer of packaging on, and they think something harmless like a thin layer of polyethylene, and strangely enough, their product is taking significantly longer to cool. And that's because the polyethylene itself isn't very thin, but it traps air between it and the outside layer of the product. And of course, air is the effective component of refrigeration. You trap air, that's how you achieve insulation. Okay, so that's important to bear in mind. If you are thinking of changing the packaging, you need to be aware that it will most probably affect the cooling process. Now, some of you may have seen this equation before. It's a simple batch chilling model, and you may have heard of these J factors and F factors. They depend on the product size, shape, physical properties, but it's just it's a way to understand the cooling process, particularly with that F factor. Now that F factor is the time required for the dimensionless temperature to reduce by a factor of 10. Now the reason we use a dimensionless temperature, it's like having a percentage. Rather than saying we want the product to cool from 25 to 21, we also would need to consider the air temperature, or the cooling medium temperature. Whereas if we define this dimensionless temperature, we know that it starts at 1 and it ends at 0, or very close to 0, regardless of the initial temperature and the air temperature. That's why we like the dimensionless temperature. So the F factor is the time required for that temperature to reduce by 10, a factor of 10. So for example, if you've got meat meat cartons entering your freezer at 30 degrees and you're cooling in air at 0 degrees, so that would be a chiller, I should say. The F factor is the time required for the meat carton to go from 30 degrees down to 3 degrees. Okay. So J factors, you can look them up, you can calculate them, and again, in the references that I'll discuss at the end, there's ways in which that can be done. Just got a typical freezing curve there to illustrate that it's a slightly different problem to chilling. These lines, the chilling process, that's actually relatively easy to model. It's this sort of behavior for the mean freezing temperature, which is a bit harder to model. So I won't go through those, just I'll point people to references if they do want to be able to work those out. Okay. So some important points to make about cooling rates. Uniformity of cooling rate can be as important as cooling time itself. And that's particularly relevant in the meat industry where you don't actually want to cool too fast. Otherwise you make it tough. You make the meat tough. At the same time, you don't want some of your, particularly if it's carcasses, you don't want some of your carcasses to be dry and tough and others to be moldy because you haven't got that rate uniform. Now, an important point to recognize is that the cooling rate is approximately proportional to the square of the product's thickness. So roughly speaking, it won't be exact. If you double the thickness, you can expect its cooling time to roughly quadruple, to increase by a factor of 4. So I'll just skip a few slides ahead. Let's say you have 2 pallets which have a nice gap between them to allow for air movement. And you say, hang on, I could squeeze another pallet in there if I just shove all those ovens over. You're going to increase the cooling time significantly because whereas you had this carton here being right on the edge, now it's surrounded by other cartons. So it's important to recognize that you don't just increase it linearly. If you increase the thickness of your product, and I mean the effective thickness, so if you have a whole lot of different cartons stacked together, you don't just double the time if you double the thickness, it goes up by more than a factor of 2. So that's why in a carton freezer, you always want them exposed on all sides. And really, if you must improve your cooling rate, under some situations, reducing your package size may be the only viable option. So another important thing to recognize trapped air is essentially insulation. So if you're putting another layer of packaging, it'll have some trapped air. It's going to be slowing that cooling rate down. Okay. Now, leading on to the next point about air movement, generally, increasing the airflow rates increases the rate of cooling. However, beyond a certain point, the cost of increased airflow will result in diminishing returns in cooling rates. So that's what we want to look at next. Air movement is very important. So this is an example of a carcass chiller which just has evaporators in one corner with the fan. One big problem is short-circuiting. So you get the air falling down and just the air around the chiller, around the evaporator, going in the circuit. And you can see these other lines just relying on natural convection. Because the carcasses are warm, you get that upwards flow of air. So ideally in this situation, a lot of research was done at the Meat Industry Research Institute of New Zealand, where I used to work, of trying to promote air movement and also air turbulence to try and distribute air evenly over those carcasses. So that's important. We mentioned before about allowing air movement over the product as much as possible. There'll be some optimization that you have to decide how much product to fit into the room, but you do need to allow for that air movement. So when we want to work out the point of diminishing returns, a very useful ratio is called the BO number. And what that does is represent the relative resistance within the product and externally to the product. Now, I've got a schematic diagram here. I've drawn a sphere, but I've also got, this is a temperature axis and then a position axis. So what I've got is 2 curves, one representing the cooling curve or cooling profile within the the solid itself, so this is within the sphere, and then outside. Those are two separate processes effectively, okay? So if you have a flat line temperature profile, that corresponds to a very high BO number, and what that's telling you is that your surface is at equilibrium with its surroundings. So there's absolutely no point trying to improve the external cooling rate. All your resistance is coming from within. So that's relevant when we're thinking about air. Conversely, if you find you have a very low BO number, it means the resistance is all external and you'll get a lot of benefit from increasing your airflow. Now generally with packaged food, we're going to be in the high BO number range. Now I'll just explain these terms. H stands for the heat transfer coefficient. If you're chilling in air or even water, the change in that number will be strongly dependent on that fluid velocity. Okay, so what I've called the heat transfer coefficient, you think of as the velocity, air or fluid velocity, air or water velocity. L is the product thickness. Now in this case it's just the radius of that sphere, but if you're having a carton, it's the shortest distance between the center and the surface. Okay, and then there's the effective thermal conductivity of the product and the packaging. Remembering that while you're, if you have frozen meat, its thermal conductivity will not be too bad. If you have air gaps, the effective or the average overall thermal conductivity will be greatly reduced. Okay, so I've just drawn a graph on the next stage which illustrates the point of diminishing return. So the BO number, you think of, again, indirectly, you can, I guess, that represents air velocity in our case, and that F factor represents chilling time. So on the scale down the bottom, you're seeing the effects of increasing the air velocity. And you can see when you've got a low BO number, so you're externally dominated, at the external heat transfer process is the restrictive one, you get that very significant increase in cooling rate. So you have the reduction of cooling time. The time required for cooling is decreasing significantly. You get to 1, so at 1, the two rates, the internal conduction, the external convection rates are about the same, or the resistances are about the same. And then the improvement with increased air velocity decreases, and it gets to about 10, and after that you're simply wasting your money. Okay, so let's look at two examples here. You've got apples which don't tend to be lined, and the air can flow through, and so you can work out, potentially you can work out a BO number for an individual product, and then you could also work out an effective BO number for it packed in a stack. The fact that kiwi fruit tend to be polylined means that rather than taking the individual apple as your product and considering the convection around it, you now have to consider that entire bag full, or the entire contents of that carton, as one product. So the conduction through from the center to the surface. So because this has a higher effective thickness, the kiwi fruit has a higher effective thickness than the apple, the maximum effective or maximum valuable air velocity will be much lower for this kiwi fruit carton than it will be for the apple. And that's, I was actually present at a PhD study recently, and he concluded just that, the student concluded just that the maximum effective, maximum beneficial air velocity was significantly lower because of the polyliner than the apples. Okay, so just pays to be aware that air movement beyond a certain point, velocity is no longer the key. It's getting that air distribution that can be as critical. So again, even in horticultural products, what you want is uniform air distribution and air movement. After a while, you can't increase cooling time with air velocity, simply because the limiting factor is now the internal, the conduction within the product. Okay, so let's look at the other side, not the product side. Now let's look at the heat exchangers. Of course, air movements, it's critical both within the store, around the condenser, around the evaporator, and then externally around the condenser. Obviously, they need to be clean, can't be blocked up. They need to be free from obstruction, from barriers, all right? Because if they're not, if your heat exchangers are partially blocked, then their effective area is reduced. Then, for example, if your evaporator is not using all its heat transfer area, the compressor will have to run at a lower, it will start to have a lower suction pressure and will have a higher duty as a result. Now, if air gets into your refrigerant system, a refrigeration system, it tends to accumulate in the condenser because often that's the highest point. And again, if you have air at the top of your condenser, it's removing a certain quantity of area that could be used for condensing your liquid. So it's reducing the effective area of your condenser. So periodically that may need to be bled. And again, we'll make that point. Often air distribution is as important as air velocity. Increasing fan speed won't necessarily improve the cooling rates. So the final issue that we need to look at is the effects of moisture getting into your refrigerated area. At home, I'm a real fridge policeman. I don't like my fridge being left open by my kids. And because you can't see it, people don't recognize that when you open your vertical fridge door, or any fridge door, but I'm thinking of the home setting, that cold air is falling out almost as if it's water. So much more dense than the warm air in your room. You're dropping all that cold air, replacing it with humid, warm air, and of course you then have to remove that and it's loaded on your defrost. So the old conventional wisdom of full refrigerators running more efficiently than empty refrigerators, well, that's supported by that understanding. If you've got it packed full of product, then when the air falls out, well, not as much air will fall out. So this is the problem. When you get the door opening, warm, moist air rushes inside, ice, frost will accumulate on the roof, on the floor, so that's a hazard. But of course, it'll condense on the product and then also on the evaporator. Now, sometimes moisture production is inevitable, unavoidable, as in the case of horticultural products. They respire. You can't do much about that, apart from, of course, modifying the atmosphere so that the rate at which they give off moisture is reduced. But it's these other factors, entering through exchange with the outside. Can't avoid that. We have to load or unload the facility. Just need to recognize that it's a very significant load on the compressor, okay? Because when it condenses on the surface, it has to reject its heat to the product, okay? Now, if when it freezes on the evaporator, it's a solid ice shell, that may not be so bad, but often it's just going to be like frost, like snow, which will trap air and again greatly reducing the performance. So that's why you need to defrost periodically. Simplest way to do that is with hot gas bypass, but that's yet another heat load. And there are guidelines for optimizing your defrost cycle. If you have good scheduling, efficient scheduling, you can minimize the number of times that product is entered and removed from your cool store, and that always helps. Other heat loads, of course, are the heated tape or heated strip around the doors to prevent them from freezing closed. So it's important to recognize that moisture management has a very strong correlation with the efficiency of your cool store. So what sort of things can you do? Well, to minimize air ingress, air entry when a forklift or a person enters some product, you can put strip curtains. Massey University did some studies about the effectiveness of strip curtains. Then of course there are air curtains, which just applies a positive pressure to prevent air being sucked in to the cool store. Obviously door seals are very important because otherwise you're getting air leaking in all the time. Now that's the evaporator fans. Of course, evaporator fans giving off heat. Make sure you don't waste money by having them going too fast, because as we said before, after a while they're not doing anything, just adding heat and costing money. Scheduling, we mentioned that before. It's very important to have effective insulation on all sides of the refrigerated area. Don't forget underfloor insulation, because in a cold store or a freezer, if there's not sufficient insulation, you'll freeze the earth, the soil underneath the store, and when something freezes, it expands and it will lift the floor. Okay, and of course if it cracks it, then that's another passage for water to come through, quite apart from any safety considerations. So very finally, we want to look at the refrigeration efficiency, best measured by the coefficient of performance, where that coefficient is the ratio of the heat being removed from your space or the product, the body, compared to the power consumption. I've got the compressor there, but it's really not just the compressor, it's all those auxiliaries. Now, it can be measured if you may already have the instruments in place, or if it's temperature, you can get away with just sticking a thermocouple to the outside of the bare pipe. So don't put it on the outside insulation, but on the bare pipe. If you can measure the temperature and pressure just before the expansion valve. Now, temperature shouldn't be a problem. Maybe pressure is going to be a bit more tricky, but you can estimate that pressure if you know the discharge pressure of your compressor. If you then know the temperature and pressure at the outlet of the evaporator pressure, perhaps the suction pressure if you've got that monitored, then if you are able to measure the flow rate of your refrigerant, if you can record the power consumption, maybe you've got a meter of the compressor plus auxiliaries, and if you get the right refrigerant property data, so if you know the refrigerant, then you can work out from the refrigerant property. So I've got a pressure enthalpy chart here. So the 2 points I was talking about, if you have it just upstream from the expansion valve, all you need is temperature and pressure, and this point is fixed. And then you can draw that down to the bottom, work out the enthalpy, and then just at the suction point for the compressor, work out the enthalpy there. The difference between those two enthalpies multiplied by the flow rate of refrigerant will give you the cooling capacity, and if you've got the power drawn by the compressor plus auxiliaries, you can get an estimate of the efficiency of your system. Now, even if you just start with a number, you can monitor how it changes. So that can be a good diagnostic tool. So if that's suddenly dropping, that indicates to you that somewhere something's not working properly, whether it's because the heat exchanger is being blocked up. It's a good idea to monitor that number so that you can assess how well your system's doing. Now, I've got over this side the top benchmark. Okay, now in reality you won't be anywhere close to COP Carnot. I've just got that 273.15, so if you use temperatures in degrees Celsius, that'll work out. That just gives you the upper limit, but rather than worrying about how close to that you are, if you monitor your COP, it'll give you a preliminary diagnostic tool to identify that something is wrong. If you want to work out where it's wrong, you really need to do some more monitoring. Preferably you'll do energy balances around those 4 units, and that will allow you to locate, hopefully, where the problem is. And therefore it'll allow you to rectify the problem more quickly if you can go right to it. Now, I know that often the refrigeration vapor compression cycle isn't set up with all those sensors in place, but as I said, with temperature at least, putting a cheap thermocouple on the outside will be a good indicator. And it may be beneficial to install these other meters, particularly if you've got a problematic system. So that's about it from me. Just to mention that if you want to know more particularly about performing calculations, whether it's chilling and freezing times or different sources of heat ingress into a cold storage facility, the ASHRAE Handbook of Refrigeration, or the ASHRAE Society, an American organization, is a good place to start. There's also the International Institute of Refrigeration. You have to pay for membership of those. Then I've written a free textbook. You just have to download it. There's a link to it. That explains, again, a bit more about those calculations of heat load and cooling time. Also, it talks a bit about cold storage of different products, etc. So that is free, but it's not nearly as expansive as the ASHRAE resource. So I've taken a bit more time than I'm supposed to, so I'll hand back to
No, you're good. All right.
Okay.
Okay, thank you, James. Do you want to just talk briefly?
Oh yeah, okay. So this is a conference which is being run in conjunction with the HVAC&R, the iRace CCCA annual industry conference, which that'll officially start, I suppose, on Friday. But we're running, International Institute of Refrigeration is running a conference at the same time. So we're going to have both an industry conference and a research conference running side by side. Interesting topics. If you're in the meat industry, I recommend you have a listen to the super chilling and super cooling technology talk. Low charge ammonia systems. Of course, low charge systems are, there's more and more pressure for refrigerant charge reduction. And then, of course, quality monitoring in the cold chain. So those are all good relevant topics for people in the industry. Some international speakers, Judith Evans, can talk about the cold chain. And then I think Rob Lamb is the one talking about ammonia systems. So if you're in the North Island, Upper North Island or Greater Auckland region, I recommend that you head over to Massey University. Starts tomorrow, but if you're just interested in the industry side, that's on the 8th. So 7th to 9th, good opportunity.
All right. Hey, thank you, James. Now, before we go over to the future webinars, I just want to pause and give you guys a chance to send in some questions. We've got a little bit of time. But just while we're waiting for anyone to send any question, James, your mention about the insulation in cool stores and how that can degrade. Would you like to just address for a minute or two some options for these guys that they can do in terms of evaluating that, whether infrared cameras or other options? What are the basic diagnostics they can go and put in place if they've got a cool store that they're worrying about or some sort of chiller? What should they be looking for? What are the telltale signs?
Well, I guess the telltale signs, if you've got a sandwich panel, often around the rivets, if you see rusting around the rivets, that can be a sign. In terms of diagnostics, though, James, I think you might be in a better position to answer that question.
All right. No. So I think obviously, using infrared to look for
hot spots,
cold spots, vice versa. Also looking at your floor, obviously. I know there are a number of people out there that I've spoken to over the last few years that have got issues, especially with aging infrastructure.
Yes.
In terms of insulation that's had water ingress over a long period of time.
Yeah.
Obviously ices up, and then obviously becomes a problem when they pops, etc. So other than what you're saying, so your normal sort of infrared plus looking for your telltale rivets sort of failing, rusts.
Yeah, exactly. Yeah.
I guess if you're trending your heating load or cooling load, you should see those things trend up as things are breaking down.
That's correct. And I guess that's the benefit of monitoring as much as you can. It allows you to identify where things are before you get to that stage. So you may decide that it's the cool store itself, rather that the room itself, rather than any individual component within the cycle that's the problem. If you find that your COP is going down, that may be poor insulation of your refrigerated space. But if you've got the diagnostics or the measurement tools to allow for diagnostics to assess each of those essential components, you rule those out, then of course you can go to the cold store.
Sure. Excellent. We have a question here. By all means, guys, feel free to fire in further questions. Roger has asked, is the Mirren's food product modeler still available? Do you know?
Yes, it is, Roger, and I'm glad you pointed that up. I should have mentioned that. For calculating heat loads and cooling times, freezing times, that is a vital tool. It's stood the test of time. It's been used over and over again. I'm pretty sure you can still buy a copy if you apply to Shane Leith at AgResearch. So if you just ring AgResearch, they still sell it. Actually, at the moment, I'm actually working with Shane. We want to try and upgrade that to a new format. So it's currently, it was written in the early 90s. It's had a few upgrades, but we want to change its format, make it more user-friendly. But I'm pretty sure you can still buy a copy. You can certainly buy the second edition, the second version, I think possibly also the third version. But yes, it's a good, robust tool, tried and trusted, been used a lot. I've got a copy myself, so absolutely. Shane Leith, okay, L-E-A-T-H.
Okay, so we'll send that out to everyone, so you've got that as an answer. So you should see that in your question and answer portal, guys. So Shane Leith at AgResearch.
AgResearch, correct.
Excellent, great. Thank you for that, James. Now another question's been posed here, James. Has there been any studies done on the use of polystyrene under concrete flooring? What is the average best thickness for this insulation?
I'm not aware of any. Yeah, so sorry, I can't answer that off the top of my head. I know that the likes of the IIR will have handbooks and guidelines about insulating cold store facilities. So I'll have to refer you to one of those, either ASHRAE or IIR, but I'm personally not aware of any studies. But I know there are studies about the effectiveness of insulation. I'm aware of studies. I can think of the person to talk to if you're interested in domestic refrigeration panels, but not about underfloor insulation in cold stores. But I'm sure it's out there. Okay, whether it's polystyrene, I'm not sure, but someone has, you can almost guarantee someone has investigated underfloor insulation.
Sure. Okay. I know certainly for buildings and the like, brands and the like of...
yeah, exactly. Yeah. But I think the general first resource, if you go to the ASHRAE website...
If you just go back, so if you just go back a slide there, James, I think...
Yeah, sorry. Yeah.
I think I need to click on the screen, perhaps. Okay.
Yeah, so if you go to that website, and if you, you know, most university libraries will have a copy of that handbook. It's an excellent place to start. And if you've got a summer student or something, good resource to hand to them, and sort of thing that a final year engineering student should be able to handle a lot of these sorts of little problems. When I was working at Mirren's, another thing that we often did was these sorts of energy audits to allow people to have some idea about the health of their system, so that they know what direction to go, where to put some effort. Otherwise, you're kind of speculating. If you're not happy with things, you don't know where to go. Whereas if you start doing some measurements, analyzing, breaking the system down, identifying where the problem is, you're going to be much further along your process through improvement.
Okay, no, thank you for that, James. So yeah, so just a reminder there, guys, you've got those resources there, and I guess in comment to your comment, James, about, you know, most university libraries. To be fair, most of these guys are out there away from the university.
That's correct. That's correct. Yeah. Yeah.
So, but having said that, it's if you've got a chiller or a refrigeration plant that you're worrying about, it's probably a good investment for your employer to
so
up and get a copy. Yeah.
That's right. Membership to those organisations, ASHRAE and IIR, will give people access to these sorts of resources. Now, what I will say is that New Zealand has a country membership to IIR. So if you look on the IIR website, you can email me, and I think my email was at the top. Was it at the top of the? You can email me, and chances are I can get you a resource free of charge. Okay, just because New Zealand pays a significant annual subscription to the International Institute of Refrigeration. So search, go on the website, see their resources, and if you want to get hold of one, chances are I can get a copy for you.
All right. So if they can't find your email, if they email me, we can point them in the right
Yeah,
way.
or else, that's right. If you go search on the university website, yeah. So by all means, get in touch if you'd like to be certainly directed towards more of these resources.
Excellent. All right, we've got a final question here for you, James.
Yeah.
This is from Ross. He's saying, wondering if you've looked at the effects of natural condensation on, say, uninsulated glycol lines. There may be a decent heat gain from this, especially if it drips off and doesn't remain on the pipe. Any thoughts?
Yeah, well, anytime you're getting condensing, and as you said, on an uninsulated glycol line, if you're getting condensing there, it's rejecting its heat to the glycol. Now, yes, if you get a film forming rather than the droplets sliding off, that's also not going to be good. Okay, but I think anytime you see condensation, that suggests that you should be insulating. Okay, I don't know if that's answered his question. Is that answered?
No, very good. Thank you very much.
Yeah. So I mean that's a good key. I mean, if you can see condensation, you know heat is ingressing. Like if you see condensation on your window, you know heat is being lost at it. Okay, heat's being lost. Excuse me. Anyway.
Yep.
Okay.
Yep. Excellent. All right. Well, thank you, James. Well, it's probably time for us to wrap up now in the absence of anyone else sending a question through. So if we just flick through a couple of slides just to... No.
All right. Oh yeah,
back one.
Sorry.
Okay, there we go. So just a reminder, guys, upcoming webinars. So in 2 weeks' time, we've got looking at process heat, sort of a level 1 or sort of a first step analysis of where to find the first level gains in your system in terms of process heat. That'll be with Tim Wormsley. Then we have Martin Atkins on the 4th of May looking at pump curves and pump sizing, the importance of getting that right. Then later on in May we've got compressed air looking at demand and needs versus actual use. Then we have flash steam, then effective fan system measurements, and then rounding out the end of the first half of the year we have a boiler corrosion and deposition failures webinar. So just to let you know, as it says there on the screen, if you go to our website energyefficiency.nz.com, under the webinar tab you'll be able to find the registration links for all of those. They'll be all sent out a couple of weeks before the webinar and sort of appropriate follow-up emails. But if you're wanting to get in and add them to your calendar to sort of make sure that you don't miss it, they're all there. You can register anytime. They're there right now. And just a reminder once more, past webinars are available on the YouTube business channel. So that's the Eka Business videos under YouTube. And yes, so once again, any more information you can email me, James N at Waikato, or we've got our website there down the bottom. And just a reminder, if you flick over if we just flick over one more page here, the Eka Business account managers and support staff are there to help you if there's something from today that's got you thinking and you're looking for where do I go to get some more help. Feel free to either contact us or your Eka Business manager. And obviously also the Eka Business website's got a number of resources that will be useful. So thank you very much for joining us today. Appreciate all the questions. But on that note, we will sign off and wish you all the best until 2 weeks' time. So thank you very much.